what we are going to discuss today is oscillators. Okay. So we're going to talk about oscillators. Okay. And specifically, what we are going to talk is how does oscillator work. Okay. So this is what's the aim for today's class. We need to understand how does an oscillator work. And based on different kinds of oscillator, we are going to just talk about few of the oscillators. Okay. So, if we just look into the use or application, okay, if you have your laptops, okay, or even the smartphones, I do know these are actually working on something which basically where there are clock signals, okay, clock signals. So these clock signals are basically nothing but an application which is based on oscillators, okay. We can also talk about radio receivers. Okay, they are also there, and they basically generate local carrier frequencies, right? Carrier frequencies. So whatever is the input frequency, based on this, an oscillator may work, okay, and it can also be based on something which we call as frequency selection, okay. So it is also used in lab signal generator. So what do I mean by that? See, in lab you have different kind of equipments where you can actually generate the waveform. Okay, one of the common apparatus might be a CRO, okay, a cathode ray oscilloscope, and so on. So these are also nothing but which are using oscillators. So if we just go for a definition of oscillators, okay, it's quite simple. You can easily remember it. Okay. So in general, the oscillator is an electronic device. Okay. Or you can say it's basically a circuit, okay, which will basically accept the DC voltage. So you can actually have a DC voltage, okay, and in return it will actually generate the periodic time varying. Okay. So it will basically have these time varying signals that are getting generated, and these are nothing but the AC signals. Okay. So you can actually have a DC to AC waveform. Okay. So the time varying, let's me write down this as waveforms, okay, of the desired frequency. So this is actually done in such a way that the desired frequencies waveform actually can be generated, and this is what is the basic definition of an oscillator usually is. So in general, if I say that I have, let's say I have got a DC signal here. Okay. So let me say I have got a DC signal. Okay. And then what I do is I feed this DC signal into an oscillator. Okay, there are different kinds of oscillators. We're going to look into that in the later classes. Okay, and if we feed it into the oscillator, we are going to finally get an AC output. And this AC output, the waveform, whatever frequency it has, will be something which we desire. Okay, whatever frequency we need, we can actually basically can get that. Okay, and this signal that we are talking about can be a square wave, okay, or a triangle wave. It depends, okay, what kind of signal you are going to generate. It depends on what kind of oscillator you are using. Okay, can be a square or a triangular wave. So this oscillator, there are different kinds, and depending on what kind of oscillator we are using, we can actually have a square wave or a triangular wave. Okay, the question is, what is the frequency range that we can actually generate, okay, depending on the input signal? And that is actually quite high. We can actually go from some hertz, okay, some hertz to several gigahertz. So that's possible. So it's basically a wide range electronic device. Okay, and this is what is the basic of oscillator is all about. But then how it's constructed? Okay, what are its major portions? That is something which we are going to look into now. Okay, so oscillator circuit, you can say in general, is an amplifier. So that means that if you have a signal and if you want to amplify that signal, that can also be done using the oscillator, okay, and then it needs a feedback. So an important point to note here would be, okay, oscillator circuit, okay, is an amplifier with a positive feedback. So by now we all know what is a feedback, okay? What you take a part of the output and feed it into the input, okay? And that is what is feedback is all about, okay? So I think we can actually draw a circuit now, okay? So that we can actually understand this. So let's just draw a very basic circuit, okay? And this might be an op-amp, okay? And I'm just saying that this is basically nothing but a part of the oscillator, and we are actually providing an input to this. I'm not showing you the inverting or the terminals, okay, we're just showing it as an device here, and then we can actually have an output at this end, right? And then we have got the flow of signal in this particular direction. Now a part of this output is basically taken out, okay, and then this is actually using this circuit, okay, we are actually feeding this back into the input, okay? We're feeding this back into the input. So we take this, okay. So this is your feedback circuit, you can say, and we can just feed it back here, okay? But then I'm just drawing these two parts separately, but because I just wanted to show you something here. Okay? Let's just look into this. So we have got an input voltage, let's say Vn, okay? Forget about it's a DC or an AC signal. We have got an input signal, and we have got an amplifier here, okay, which has got a gain, okay? It has got a gain. So that means whatever output we have, whatever output we are going to have will be nothing but this gain factor of this op-amp, let's say, into the input voltage. So this will be the output. So that means we are getting a gain of it, okay? So if a part of it is taken out, okay, and then we are actually having a circuit, and let's say the gain of this particular circuit is, let's say, beta. Okay, this is the same A and beta which we have studied before also, okay? So this VF, that means this is your, let's say this is your feedback, okay? So let me just might mark this as feedback. So this is your feedback circuit. Now you have taken a part from here, okay? So that means you have taken output, okay, and then you have got it back into the input, okay? So let's say what I can say here is that this VF, which is nothing but the feedback voltage, is nothing but beta, okay, which is the gain of the feedback circuit, into V naught. V naught means we are talking about V output here, okay? V output. This is V output, okay, just written it here, but it's the same thing, okay? So in general, what we can say is we can simply write it down as beta into V out, okay, sorry, okay, let's not write down V out. What we can do is we can just replace this relation for V out that we have already. So we have got beta into A, okay, into V in. So this is the feedback that we actually have from this particular circuit, okay? So there are certain conditions based on which this feedback circuit will actually work, okay? So if I write down one point here, which is actually important, this V out, okay, if this V out, if V out, okay, is in phase. So, you know, if you're not putting it into the if you're putting the input as the non-inverting terminal, if you're considering this to be an op-amp, and if you're putting it into a non-inverting terminal, this Vn and V out will be in phase. If it is in the inverting terminal, it will be 180-degree out of phase in an op-amp, if you remember. So if this V output is in phase with V input, okay, then what happens is then feedback is also in phase with V in, right? So what do I mean by this? It simply means that if V out, okay, let me write it down here, V out is in phase with V in, then the feedback is also in phase with V in. So that means if you're basically having a signal, something like this, which is there, and then you have got the output, which is this, maybe amplified, but you see both are in phase, okay? I'm not taking it as out of phase. If this is like this, that means this is 180-degree out of phase, right? So I'm not saying that this is out of phase, I'm saying that this is in phase. So if this is in phase, whatever you have here in the feedback circuit will also be in phase, right? This will be also in phase. So that means the input that we are providing via the feedback circuit will also be in phase. So this is what it means. If V out is in phase with V in, then feedback is also in phase with V in. Okay? So this is something which is important. Okay. So now what happens is that, let's say I have taken a feedback from the output and I have removed V in. Okay, what's going to happen? So let's just try to understand this. So let's say I have, okay. So let's say V feedback. Okay, let me write it down as feedback here. Okay, is fed as an input. Okay, signal, and V in, okay, is removed. Let's say. So we have removed it. Okay, so this is this. So we are defining a different condition now here, and which we call as the sustained oscillation. Okay, so after feedback, okay, we should have got something which we call as sustained oscillation. Okay, will and sustained oscillation. So the question is, what do I mean by sustained oscillation? Okay, before I proceed, okay, I will tell this and then I will explain again. So suppose you have got an input something like this, okay, and then you see the output will keep on having this feedback, and it will be something like this, okay, and it keeps on going with the same amplitude. That is called sustained oscillation. In case you are having a signal which is actually rising and then slowly starts falling, okay, this is not sustained oscillation. On the other hand, if you have got a very small signal which actually slowly starts to give you the higher amplitude, this is also not sustained oscillation. Sustained oscillation is the amplitude will be more or less remaining fixed. Okay, this is something which we should understand in case of sustained oscillation. Okay? So this is something which we want to look into. So just giving you this definition of sustained oscillation. Okay, this sustained oscillation that we are actually talking about, okay, will depend on, okay, A into beta, okay, A into beta, and A into beta is basically called as loop gain. Okay, so this A beta will define whether you are having a sustained oscillation or not. Okay, and slowly we are going to see that what exactly should be the value of beta based on which we can say yes, we are getting a sustained oscillation. Okay, and then the amplitude doesn't die off. So that is important. Okay, so in general, if we say if this A beta, okay, is less than 1, okay, then what happens is eventually the signal, okay, signal will die out. So we'll basically have a drop in the signal if this A beta is less than 1. So the loop gain needs to be, should not be less than 1. Whether it should be greater than 1 or not, we'll come to that later. So what happens is, if this is less than 1, okay, you are going to have a signal which will eventually die off. Okay? You're going to have a signal which will eventually die off. So if I have a very high amplitude at the beginning, so if you remember your lower classes oscillation and all, you must have studied about this, which you call as damping, right? So this is what is going to happen if A beta is less than 1. The question is why and how. Okay, this is something which we are going to come to. Okay? So let me just take this example maybe, okay, and then this will be very more clear. Okay, so let this A beta, okay, be 0.9. So let's say this A beta is 0.9, which is less than 1, okay, and then we are actually applying an input voltage V in, which is equal to nothing but, let's say, 2 volt. Okay, so therefore if we just go into the previous diagram, I think I've already told you this, look here, V feedback voltage is nothing but beta into A into V in, beta into A into V in. So if we just write down this V feedback, this is A beta V in. So if this is 0.9, that means this is 0.9 into 2, which is simple, nothing but 1.8 volt. So you see the input voltage and whatever we have got after it was fed through the feedback circuit is 1.8 volt. That means the amplitude has decreased. Okay, so therefore we can simply say that amplitude decreased. So we cannot call it as sustained oscillation. Okay, so there is also this another important logic that when this a beta is greater than 1, so what happens is when a beta is greater than 1, the amplitude that we are talking about here will increase. Amplitude increases. This is also not sustained oscillation, as I said. So this is also not there. Okay. So hence for both a beta greater than 1 and a beta less than 1, we don't get sustained oscillation. Okay. So if I just write down here for a beta greater than 1, a beta less than 1, okay, 1 looks like that 2. Yeah, we don't get sustained oscillation. So what is the condition? The condition is a beta must be equal to 1. And then only we can say that we are actually going to get sustained oscillation. Okay? So for these cases, we are not getting sustained oscillation. Okay, if a beta is equal to 1, okay, Vf, the feedback will be equal to V in. That's quite obvious, right? Because if you look into the formula, this is equal to 1. So this Vf and V in are equal. Okay. And then we actually get something which you call as hence sustained oscillation. So sustained, you know, the condition is still maintained. Okay. Sustained oscillation. Okay. So please note down this factor because there is a very important question coming up which I'm going to write. Okay. For your exam, this is important. Okay? Can be an objective question. Okay, and then the heading for this is condition for sustained oscillation. So I think you have already I've discussed enough of this. If I ask you to discuss the condition of sustained oscillation, probably you have to do whatever we have done till now. But if I'm asking you only say what are the conditions for sustained oscillation, you have to write down whatever I'm going to write now. Okay, and it will be basically just a 2-mark question. If you want to explain, and if I'm giving you a question of explanation, probably the marks will be. So there are usually 2 conditions. Okay, and I think you by now you could have already guessed it. Okay, the first condition is that this a beta must be equal to 1. That is the first condition. Okay, and then the phase. Okay, the phase difference. So we can say the angle because of this feedback circuit should be equal to 0. There should be no phase difference. Okay, or we can say basically no phase shift in general. Okay? So we can say no phase shift. Okay, so this is very important. So these two actually are the conditions, okay, for sustained oscillation. Okay, and what they are called is this. So I think this is also something which you should know if this is asked, and this is actually quite a common question even for your entrance exams and all. Okay, so these are called Barkerson criteria for oscillation, okay, or sustained oscillation. Okay, so this is important. So this phase shift, it means that whatever phase shift is being offered by the opamp, okay, or by the amplifier, we can say in general, and the feedback circuit should more or less be 0. Okay, and this is actually called the Barkerson criteria. So this is important. So please remember this. Okay, will be a 2-mark question. It's a very simple idea. Okay, and if we are doing any course of electronics and we are talking about oscillators, this is an important factor. Okay, something which is quite interesting is this. Okay, what happens is sometimes even if there is no input, still you might be getting some signals which gets amplified. The question is how. We don't have any input, but still we can have signals which can get amplified. There are certain reasons for this, because you cannot have an output without any kind of input, right? But we are going to get that, but that is because of something which we call as thermal motion. Okay, this is something which we are going to discuss now. So amplified signal, okay, without input. Right? So how we are going to get that? Okay, so let's see. So there is, if you consider any kind of electronic device, there will always be some kind of thermal noise. Okay, so if you're putting it into room temperature, if the temperature is there, there will be this thermal noise. That means there will be constant motion of the charge carriers, based on which you are going to get some kind of an output from the circuit system. Okay, and this is basically something which gives rise to some unknown, unwanted signals. Okay, so that is why we basically call them as noise. So thermal noise basically consists of all frequency components. It will have all frequency components because it's random. So we really don't know what kind of frequency it will basically give out. But you have to remember that the feedback circuit is working as a frequency selector. So sometimes whatever frequency it might be, it will actually select one of the frequencies and that will be actually amplified. Okay. So what happens is, let's say we are actually tuning in the oscillator, right? So when the oscillator, okay, is turned on, these noises that we are talking about gets amplified. Okay, because thermal noise, okay, amplified. Okay, even without input signal. You have to understand this, even without input signal. So even if you are not giving any kind of input signal, this will actually get amplified. Okay, so this noise, whatever we have, this noise is given back to the feedback circuit. So the feedback circuit will actually take this noise, okay, as a signal, okay, and try to amplify it. Okay, it will try to give this back to the input. Okay, but this feedback circuit that we're talking about is basically not working for all frequency. It is basically got a certain specific frequency selection criteria. Okay, so this feedback circuit that we're talking about, okay, feedback circuit, okay, is a frequency selective circuit. You have to understand this, frequency selective circuit. That's why it will basically amplify only a signal of a particular frequency. Okay, so what happens is only for one frequency, okay, only for one frequency, phase shift will be 0. So basically, or since if you're talking about oscillations here, you should have the phase shift being 0. Only for a certain frequency, the phase shift will be 0. It won't be 0 for all the frequencies. Okay, and this frequency where the phase shift is 0, this signal will be amplified. So you can have a signal even without an input. Okay, so if we really want to talk about this in terms of mathematical expressions, what we can say is this. Okay, so we basically have at the input, okay, let me just repeat whatever we have done here. At the input, we have got the V in, which was the input which was given originally, plus whatever is given via the feedback circuit, plus Vf. Okay, and we already know that V out is equal to the amplification factor or the gain factor into whatever is the input. But at the input, we do have the input plus the feedback. Both we have. Okay, so this is what is happening in general. Okay, but then we already know. I think I've already showed it to you in the diagram, but let me just repeat this again. Okay, but VF, V feedback, is equal to nothing but beta into V out, right? This is something which you already have seen. That was actually a part of the feedback circuit that we have. Okay, so therefore, what we can say is that this V out that we are talking about, okay, is equal to A into, in case of VF, we can write down beta into V out. So we can simply write it down as V in plus beta into V out. This derivation is important. Please take care of this. Okay, so if we just try to simplify this is V out, this is also V out, so this is A beta, right? So what you can do is you can simply write it down as V out, okay, into 1 minus A beta, take it common, is equal to A into V in. Okay, so if I just want to write down a general description of this, okay, if a general expression for this, we can simply write it down as V out by V in is equal to A divided by 1 minus A beta. Please try to remember this relation, okay, important, and how to derive it, you know it, okay. So if I ask you to derive this relation using a circuit diagram, the previous circuit diagram you have to draw and try to derive this out, okay, and we are going to understand something from here. Okay, let's mark this as equation 1. So equation 1 was V out divided by V in is equal to A divided by 1 minus A beta. Okay. Now look into this condition here. Okay. Now we are going to talk about if there is no V in. Okay. So even without V in, right? There is no V in, oscillation exists, right? So we still have the oscillations here. So look here, that means on this particular part, we are saying that V in is equal to 0. Now this V in is equal to 0, V naught divided by 0 is something which is not defined, right? That means on this side also, this denominator should be 0. Then only this condition will be satisfied, okay? So in order to satisfy this condition, okay, let me remark this as equation 1, okay? For satisfying, this is mathematical, okay? Equation 1, A beta must be equal to 1. If A beta is equal to 1, this is 1 minus 1, which is 0. This side also 0. That means we have got a certain equation which is actually valid under this condition, okay? And that is the reason that A beta must be equal to 1 when we are talking about sustained oscillation, okay? So this is only satisfied when A beta is equal to 1. So this is important. So you can also prove this condition for sustained oscillation. But then for that, first you have to know what exactly do we mean by sustained oscillation. Okay. So in order to prove this relation, we have to know that even without an input, we are going to get an output. Okay. So this is what is important in this case. Okay. So this is what is an oscillator is all about and how exactly it works. Okay. And in the next class, we are going to look into different types of oscillator, okay? And some of the oscillators we are going to study, okay? There are sinusoidal oscillators as well as there are non-sinusoidal oscillators. So